This conference will now be recorded.
Okay. 45 people have joined. Recording is going on, right?
प्रॉब्लम यही है कि नहीं जाता।
But the screen. Hello, everyone is there?
No, sir, but they'll eventually join in.
How many have come? Still 45 people, right?
Yes, sir.
Shall we start?
Yes, sir. Please.
Now, are you able to see the screen?
Yes, sir.
It's not moving. Okay, is it visible to all of you, right?
Yes, sir.
Hello. Yeah. Okay, fine. So today we are again. I'm starting that your antihistamine topic from medicinal chemistry. Why? Because I would like to repeat this slide what we have discussed in previous class. Because some of you might have missed that class one. So without that, it won't be possible for you all to understand the antihistamine concept. So starting with the today's classes, we'll talk about today antihistaminic agents, unit 1. Under that we will discuss again, we will repeat, in fact we'll repeat histamine's introduction, its biosynthesis, its biological role, the receptors involved in histamines, and how to metabolize the histamines, how to abolish the action of histamines. We'll talk in brief about the chemistry of histamines. We'll talk about its isomerism, and other aspects. So let us starting with the topic histamine first. What does it mean? See, chemically, histamine is 2-imidazole 4-bial ethylamine or beta imidazole ethylamine. That part we'll discuss in later. But what actually biologically histamine is? So histamine is nothing but they are a biogenic amines. You can say histo means tissue or amines. So amines produced by tissue in the body. So these histamines, they are produced by tissue, and mostly the mast cells, the Golgi complex. All of you know what is the Golgi complex. The Camilo Golgi, which identified this structure in a cell, and it is involved in excretory as well as a lot of biochemical reactions. So histamines are also synthesized by this Golgi complex of mast cells and basophils by decarboxylation of L-histidine. So if somebody asks what is the precursor amino acid or from where histamine is synthesized, like in exam, no, you can have MCQ questions, which of the following amino acid is used to synthesize histamine. So remember, it is L-histidine. You can see the screen here. This is L-histidine, an amino acid, heterocyclic amino acid containing 2 nitrogen, one is with hydrogen, another one is containing the double bond. And this imidazole ring actually is a heterocyclic imidazole ring which is containing ethylamine group and one carboxyl group attached to 4th position of this imidazole ring. So histidine is basically 4 substituted imidazole ring with ethylamine and carboxyl group. This L-histidine, it undergoes decarboxylation. The enzyme is here, you can see L-histidine decarboxylase. This L-histidine undergoes decarboxylation catalyzed by pyridoxal phosphate, and under this influence of pyridoxal phosphate, L-histidine loses its carboxyl group here minus CO2 and it gives histamine. Now there is not much difference in the structure. If you see carefully, this L-histidine and histamine, the heterocyclic part remains the same. You can see here, this carbon, these 2 carbons are same. Amine group is as such. Only this carboxyl group has been removed. It is not in the histamine. So very simple structure. In fact, you can easy to remember for us. L-histidine, remove the carboxyl group from L-histidine, it becomes histamine. So histamine, a biogenic amine, a chemical messenger synthesized in Golgi complex of mast cells and basophils by decarboxylation of histidine, L-histidine. Remember L-histidine, why? Because in previous class we have discussed that tissue or cell, they take only L form of the amino acid, they do not take D form of amino acid, and that's why only L-histidine is consumed for the preparation of histamine. Now the next is the where they are located. The histamines actually found in almost all parts. It is widely distributed, but their concentration is seen maximum in case of CSF, cerebrospinal fluid, skin, mucosal cell of bronchi, that is your lungs part, intestine and urinary tract. So most of the antihistamines which we will discuss in our next class is related with these parts or the functions or the abnormal functions which is manifested by the release of histamines. Those antihistamines usually work or the block the activity of these histamines. So synthesized histamines, they stored in the mast cells and localized in these parts of the body, like in these cells, mucosal cells, CSF, bronchi, intestine, urinary tract, GIT and all those. Now once they are stored, they get released. See, the very short lifespan they have to get released or they will get metabolized automatically. They will undergo a metabolism and they will give the different compounds depending on the which type of reactions it is undergoing and what type of enzymes are involved. So the synthesized histamines, they are getting released from the mast cells by a stimuli. Stimuli is nothing but an external what you can say we are inducing the cell or the cell is getting exposed to the external factors, and that is stimulating the release or stimulating the mast cells to release histamines. That stimuli may be immunogenic, antigen antibody reactions, or it may be non-immunogenic. If it is non-immunogenic, it may be dust, heat, anything it can be, correct. Then any xenobiotics, any drugs taken. Xenobiotics are the term usually used in medicinal chemistry for the substances which is taken from outside. So any foreign matter in our body is called as xenobiotics. So the release of histamine can be catalyzed, or it can be possible by any kind of stimuli, any external factors. It may be immunogenic, it may be non-immunogenic. Any factors which is leading to the immune reactions, it will cause the release of histamine, or it may be non-immunogenic, such as dust. We say no, I am allergic to heat, or I am allergic to particular chemical. So these are nothing but the stimuli. You can say these stimuli, they force the mast cells to release the histamines, and then we get the different signs and symptoms appears in the body, which we say it as a allergic reactions. So these all allergic reactions are nothing but due to the release of histamines, and then histamines binding to the particular receptors and eliciting or producing that effect. You can see here histamines in this diagram, that histamine is getting released from mast cells. It is binding with different receptors. For example, here H1, 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 H2, H1. There are other types of receptor also. This is just one representation. So these receptors, when they bind, the histamine binds to these receptors, they produce the respective or biological functions. Or you can find out some, like increase in hydrochloric acid secretion or gastric acid secretions, increase in peristaltic movement of our intestine, then bronchoconstrictions, produce formation of cough and all those, then CNS stimulations, depending on which type of receptors it has occupied most. It is not always necessary that once histamine released, it will produce the all these effects simultaneously. It depends. Suppose if histamine binds more with the H1 receptors, which form of histamine is responsible for binding to the histamine receptors, we'll discuss in coming slide, then it will produce that particular effect more. But in general, the released histamine, for example, you can see in this diagram, if they are binding with H1, they will produce the pharmacological effect, or you can say the biological effect related to H1 receptors. If they are binding with H2 receptor, the activity will be related to that one. Similarly, H3 receptors, and nowadays H4 receptors research is also going on. So here you can see in central nervous system, they also produce their effect. In this diagram, you can see here histamine binding to H2 receptors and producing the secretion of hydrochloric acid through parietal cells of stomach. So these are the things which is metabolized, mediated by the histamine. So we can say that, in short, from this slide, what we can conclude: histamine, a heterocyclic moiety containing imidazole ring. You can see imidazole ring, one nitrogen here and one here, 1, 3, 5. Remember always 5-membered heterocyclic molecule containing 2 nitrogen, both at first and third positions. They are called as imidazole. So in this structure, you can see one nitrogen is here, another is at third position. So 1, 3 means it is imidazole ring containing ethyl amine group at its fourth position. That is the histamine. How histamines are synthesized? They are synthesized by a simple decarboxylation reaction of L-histidine amino acid. It is an essential amino acid. Remember, L-histidine amino acid loses its carboxyl group under the influence of pyridoxal phosphate and catalyzed by enzyme L-histidine decarboxylase to give histamine. These histamines are mainly synthesized in mast cells and basophils. The Golgi apparatus or Golgi complex or Golgi body of the mast cells or basophils, the histamines get synthesized and stored in most of the body part, but their concentration is seen higher in cerebrospinal fluid, skin, bronchi, the respiratory system, intestine, and urinary tract. And you will even, in fact, you will find all those antihistamines which is in the market is related with the abnormal function of these parts of the body only. So once the histamines are synthesized and stored in the body, they get released because they have very short span of time. If they are not getting released, then they will undergo metabolism and they will get deactivated. Correct. So it is a continuous process. They are getting synthesized and getting metabolized. if your body is getting exposed to any kind of a stimuli, any external factor, maybe immunogenic reactions, maybe non-immunogenic factors, which is called as a stimuli, the histamine will get released from the mast cells, which you can see from this diagram here. The mast cells having the histamine granules, the granules containing histamines, it will release it, and the released histamines will bind to the respective receptors and they will produce the biological effect. Hope till here it is clear. Any doubt? Please say yes or no. If you have doubt, we'll clarify one by one from this slide. So any questions from this slide, please discuss. Yeah. Anyone from the group? Or shall I move to the next slide, or do you have any doubts from this slide?
No doubt.
No, sir, no doubt, sir.
Is it clear?
Yes, sir.
Yeah. So then we'll move to the next slide. The next part of this class is physiological role of histamines. So what histamine? Sorry, one second. What histamine will show means physiological role histamine will produce and how it will produce. So the histamines, as I discussed in previous class, the histamine released after the stimulations. It may be external stimulation, which may be immunogenic, or it may be due to triggered maybe due to non-immunogenic reactions. So those stimuli causes the release of histamines, and once the histamine release, it plays multiple biological role through its G protein coupled receptors. So sometimes in exam or even in Viva, teachers ask that what are the different types of histamine receptors. So you remember there are 4 types of histamine receptors basically, but right now our antihistamine discussion in this medicinal chemistry portion will be restricted mainly to H1 receptor and H2 receptors. Some 1 or 2 examples we'll discuss about H3 receptors. However, H4 is not that much pharmacologically significance. It is a point matter of research, but right now it is not that much important for us. So we'll concentrate our research on H1 and H2 receptors mainly. So, but we should know what are the 4 different types of histamine receptors. So H1, H2, H3, H4, and remember each these 4 receptors, they have different functions, and they are localized in different cells, different parts, and they see all these receptors are protein, right? They are proteinous in nature. They have certain conformations. They have their own orientations, and based on that, they bind to the particular drug. And this is the reason for, or this is the logic behind the selectivity of the drug for a particular receptor. One antihistamine doesn't mean that it will bind to all 4 receptors, H1 or H2 or H3 or H4. If you are designing any drug which is having affinity for H1 receptor, it will only abolish, or it will only block the effect of histamine which is related with H1 receptor. This should be very clear to all of you. Antihistamine doesn't mean, or even any drug, it doesn't mean that it will bind to all receptors. There's nothing universal, correct? It will be the function of the particular drugs what we synthesize, design is highly selective, target specific, and they produce only the pharmacological effect for which they have been designed. So here also histamines, depending on the affinity for the receptors, they produce their respective pharmacological effects. If they are binding with H1 receptors, they will show their effect, especially related to gastrointestinal tracts, and they in the brain they have the effect, and in the stimulation of cough receptors, they causes hypertensions, they causes flushings, bronchoconstrictions, then pain. All those things will be mediated by the H1 receptors. So when you are taking histamines which will bind to H1 receptors, these abnormal effects can be blocked or can be suppressed. If suppose someone is having the cough, severe cough, so you need expectorant, right? Or if we are talking about the expectorant, we have the expectorants which contains histamine antagonist, H1 receptor antagonist. Those things will talk in our when we will start the topic antihistamines from the next class. So I mean to say that all the histamines produced in our body are released from the mast cells and basophils after stimulation or the external stimuli, maybe immunogenic or non-immunogenic. That histamine binds to the specific receptors, either H1, H2, H3 or H4, and only produce or only suppress that abnormal effect for which it has been designed to do so. Pharmacological point of view, out of these four receptors and multiple biological effects mediated by histamines, these three are important, and for these three effects, hypersensitivity and allergic inflammatory reactions, regulation of gastric acid secretions, neurotransmitter in the central nervous system. So what antihistamines used nowadays clinically are mainly designed to suppress these functions which has been mediated by excess release of histamines. Okay, so remember, if histamine is not getting released, if we are in the well conditions, no stress, no any kind of allergic like no exposure to any chemicals, any stimuli, no any kind of antigen antibody reactions, then histamines won't be released and it will get metabolized automatically. So it doesn't mean that if histamines getting synthesized will get released all and it will produce the effect always. No, it is not like that. So now it's clear, histamines produce their effect by four receptors, H1, H2, H3 and H4. So we should know when we'll go for the antihistamine, we must have the idea about the histamine receptors. Okay, is it clear? Any doubts from this slide?
No, sir, no
Hello?
doubt, sir.
Okay, shall I move to
No,
the next one?
Yes, sir.
Yes, sir.
Yeah, fine. Yeah, thank you. Coming to the next slide, what we are going to discuss is the chemistry of histamine. Till here, what we discussed, we discussed about the histamines biosynthesis. We discussed about the receptors to which histamine binds. We discussed about the biological role produced or mediated by histamines. Now let us talk about some chemistry of the molecule. So now we all know that histamine is a heterocyclic moiety, correct? It is containing imidazole ring. Imidazole ring is substituted with ethylamine at its fourth position, right? Till here we know. Now next question is, which form of histamine is active? Does histamine, since it has so many functional groups are there, so many protons are there, is there any changes in the structure? Is there any possibility of isomerism, or is there any possibility of losing or gaining of protons, protonation or deprotonations? All these things we will discuss in this slide. So coming to the property of the physicochemical property of histamine, if we see the structures, we find that there are three nitrogen group in the structure. Two in the imidazole ring, you can see here, and one NH2, which is the ethylamine chain. So one primary amine, two heterocyclic nitrogen, one nitrogen with primary amine and two heterocyclic nitrogen present in histamine. So neutrals, I'm not talking about right now, physiological or in body. If you say histamine, in general, it will be a basic molecule. But under physiological condition, it undergoes protonations and it becomes monoprotonated, and the monoprotonated histamine is responsible for the biological activity, responsible for the binding to the receptors. So you can see here NH2, in the previous structure we have seen the NH2 get protonated to NH3 plus, and the overall pK value of histamine is 9.40. Now you can see all this is the overall pK value, but all these three nitrogens are contributing different. They are like N pros 5.80, N tele tele 9.40, and in alpha, that is your NH2 part, is having pK value of 14.0. So based on these pK values, we can say that histamine is a basic molecule and it exists in a monocationic form at pH 7.4, which is nothing but the physiological pH. So in our body, the histamine exists in this form. You can see where NH2 has got protonated and the pK of molecule is 9.40. Now this is something which can change. Which can change in the sense if you are increasing the pH or if you are continuing the protonation, the histamine will exist in diprotonated form. So you can see in this next structures, this pK 9.40 where only NH2 has been protonated, it is in the another structure, the another nitrogen got protonated, this one, and its pK is coming down, which is 5.80. Now how and why the pK is coming 5.80 here? Why? Because as you are introducing more protons, see, remember these things are like NH3 plus, here NH plus, these are not a permanent thing. It means the proton coming here will leave the molecule very easily, and that's why this structure, and this structure will exist in equilibrium with the normal histamine. It means these are not a completely ionic reactions. They are just the temporary sharing of proton. The proton first getting shared by the NH2, taking proton, base having the ability to take the proton. So that's why NH2, that's why NH2 will take this proton and it is becoming NH3. But if the reaction condition is unfavorable, this NH3 will release its proton and it will become normal histamine. Similarly, when you continuing the protonation, this histamine is taking another one proton and it is existing in the diprotonated form. You can see nitrogen with positive charge. But from our pharmacological importance, the monoprotonated histamines is only active and it only binds to the receptors. However, there will be equilibrium between monoprotonated and diprotonated form, but the equilibrium should always shift towards left hand side, not towards the right hand side. If it is going towards the right hand side, it will not bind to the receptor. Now coming to the tautomer of histamines, what are the different tautomers of histamine are, and in how many tautomeric form histamine can exist. So in exam in MCQ, the question may appear, how many tautomeric form of histamine is possible? So histamine exists in 2 tautomeric form. You can see in the structure here. Now this 2 tautomeric form is just because the intramolecular shifting of hydrogen from 3rd position to 1st position. Now you can see the structure. If you carefully, you can see here. See, this is the tele and this is pi pros. Now tele and pros, these 2 notions given to this nitrogen is with respective position to this NH2 group, alpha amino group. The nitrogen, remember the nitrogen which is close to this alpha amino group is given the notion pros. It is called as pros, means near, and the nitrogen which is far away from this alpha amino group is called tele. In previous class I had discussed this one. Tele means far, telescope, telegram, correct. So this nitrogen which is away from this alpha amino group, they have tele notions. It has been assigned as a tele, while the nitrogen which is close to alpha amino group assigned as a pros or pi. So this tele and pros, these 2 nitrogens, they exchange, or the hydrogen is getting interchange between these 2 nitrogens. Remember, in tautomeric form the alpha nitrogen is not involved, so don't get confused that from here again this hydrogen will go to this nitrogen. No, it won't go. So it is just the shifting of hydrogen from tele nitrogen to pros nitrogen to tele nitrogen, and existence of another tautomeric form. You can write histamine structure in any form. Either you can write this way or you can write this way. but for the sake of stability, sometimes we prefer to write the structure in this way. However, there is no any such rule. You can write any one structure is good for if you are sticking with either this or that one. So the question is now here, how many tautomeric form histamine has? Histamine has two tautomeric form, and what is the reason for that? The reason for this two tautomeric form is the intramolecular shifting of hydrogen, or better you can say proton, from tele nitrogen to cross nitrogen, or from third nitrogen to first nitrogen, or first nitrogen to third nitrogen. Because of that, this tautomeric form will exist. Remember, in this tautomeric form, the alpha amino group is not involved anywhere. Now, question here can be asked that what is alpha amino group? The amino group attached to the alpha carbon. Or what is alpha carbon? If somebody say the carbon which is next to the functional group. This is about the tautomeric form. Now let us come to the conformational isomers or rotamers of this histamine. In how many ways the molecule can rotate or the molecule can twist? What are the different possibilities? So we know there are different types of isomer, right? All of you have studied in your basic organic chemistry. I think in POC 1, maybe you must have idea, or in your POC also you must have studied about the isomerism. So we know there are different types like geometrical isomerism, functional isomerism. Under that again, functional structural isomerisms. Under that, functional, positionals. There are different types. Then we have one type, geometrical rotation around carbon-carbon double bond due to that, and then we have one type called conformational isomerisms. Now this conformational isomerisms, the compounds, resulting compounds are called as conformers. And remember one thing, the difference between this conformational and geometrical is that you can isolate or separate two geometrical isomers. They exist as a different compound, like E and Z, cis trans usually be assigned. But in case of conformers, they just exist in it's a hypothetical concept. They exist in equilibrium, and just because of they are rapidly interconvertible to each other, and this is because of the low energy associated with the rotation between the two carbon. So all these conformational isomers here in case of it's called as rotamers is just because of the rotation between carbon single bond. So here you can see this structure. For example, this one carbon, alpha carbon, beta carbon, two carbons are there. So now this beta carbon is attached to the imidazole ring, while alpha carbon and beta carbon, they are attached together. So this molecule can rotate. If somebody asks how many possibilities, so we can say, okay, one rotation will be between alpha and beta carbon here, and one can be here. But the rotation between this imidazole ring and carbon is not easy. It won't possible, or it may consume large energy, means you can say energetically not allowed. So that's why this angle, theta angle here is 0 for this rotation, while the rotation between carbon is possible, carbon single bond rotation, and it rotates with 180 degree, giving to another conformation, another rotamer of histamine. So due to these two rotations, histamine, due to this rotation between carbon double bond, rotation between alpha carbon and beta carbon, the histamine has two conformers or two rotamers. One is trans, where you can see the theta 2 is having 180 degree, while another one is gauge. And now what is trans, what is gauge, you must have studied, correct? Because POC 1 is over. So if we go in deep here right now, stereochemistry, we might deviate from the topic. So we can see in this histamine structure, it is clear that we have two types of rotamers, two conformational isomers due to the rotation between the carbon single bond. Remember, my dear friends, if you are having carbon double bond, It is very difficult to rotate, the two aromatic system directly attached to each other through any linker, any carbon, but it is very easy to rotate the two aliphatic carbons. So, and because of that, we are getting the two different rotamers or two different conformers of histamine. You can see here theta 2 here is 60 degree, while in this case theta 2 is 180 degree. This one can be also better explained by this representation. Here you can see this amine group and NH imidazole ring and protonated NH3 or NH2 group. Let us talk NH2 group. They are far apart from each other. Correct? They are trans, far apart from each other, and that's why their theta 2 is 180 degree. But in case of another structure, Gauge structure, you can see that NH2 group of histamine and the imidazole ring, they are close to each other, having Gauge conformations. So from this slide, what we came to know that first point, histamine in physiological condition exists as a monocationic form. Correct? Histamine is a basic molecule. Physiologically active histamine has pK of 9.40. If you keep increasing the protonation process, it will exist as a diprotonated form, which is here, but the pharmacologically active form is this one, pK 9.40 monoprotonated. Now, what we also came to know about the tautomerism in histamine. Histamine molecule undergoes tautomerism, and that tautomerism is just because of the intramolecular shifting of proton from telenitrogen to the pros nitrogen. Telenitrogen means nitrogen 3 having the symbol of tau, and nitrogen 1 symbol pi. Why the word tele and pros I am using is because the nitrogen which is close to this NH2 group is pros, the nitrogen which is opposite from this NH2 group is tele. Tele means far, and the proton shifting takes place between this nitrogen tele to pros and pros to tele. Interchanging takes place, and it exists in tautomeric form. So the NH2 group is this aliphatic NH2 group, amine, ethylamine group is not involved in tautomerism of histamine. These are the basic things you must know in chemistry, so you should not get confused. Now we discussed about the tautomers or conformational isomer or rotamers of histamines. We discussed that histamines having exist in two conformational forms, and that two conformational form is because of the rotation around carbon single bond, and each conformation has different value of theta angle, that is the carbon bond angle. In first structure we can see theta 2 is 180, in second structure it is 60 degree. In both cases we cannot rotate this point and this carbon, but rotation can be done at this carbon, and due to the rotation at this carbon we have two different types of structures. The rotation at 180 degree is having imidazole ring and NH2 ring is far from each other, while the rotation having 60 degree angle is having close to each other. One is called as gauge, one is called as trans. Okay, so any questions from this slide? This is very important slide for the chemistry of histamine. If you have any query, please clarify it before I move to the next slide. Yes, please. Any questions? Hello.
No doubt, sir.
Yeah, anyone
No,
from? No, is it clear?
Yes, sir.
Yeah, okay. Fine. Then we'll move to the next slide, because after this, no, we won't discuss histamine. We'll next class we'll directly go to antihistamine. So I am explaining in brief. Okay, coming to the next slide. Termination of histamine action. So how histamine action can be terminated? Correct. Or what are the different approaches which can be followed, or which is usually used either by the cell itself or by the person who is having that problem related with histamines. So basically there are 5 approaches you can see here: blocking the cellular uptake, then desensitization of cells, towards histamine, then metabolism of histamine, or blocking the release of histamine, blocking histamine binding to a receptor. So there are 5 approaches by which the effect of released histamine can be nullified, can be abolished. The first one is cell blocking the cellular uptake. So in this one, the cell itself they modify themselves and they stop using the released histamines. They stop absorbing the released histamines. This can be also achieved by desensitization of cells. The certain cells they become desensitized. Now see these point 1 blocking the cellular uptake, point 2 desensitization of cells, and point 3 metabolism of histamine. These 3 are, you can say, as the defense mechanism, or you can say auto-regulated. If the concentration of histamine is too high, if someone is getting exposed to the allergic conditions, to getting exposed to the stimuli, the cell may develop the mechanism and they may avoid histamines themselves. So in these 3, the role of a drug discovery, like a medicinal chemist or a pharmacist, is not that too much, correct? So the cell themselves they stop you absorbing the histamines, or they themselves make them less sensitive towards histamine. And the third approach followed by cell is the metabolism of histamines. Then the fourth is by blocking the release of histamines, which can be achieved by using the different now so many drugs are available. And fifth approach is blocking the binding of histamine to respective receptors such as H1, H2, H3. Depending on which type of receptor needs to be blocked, that type of antihistamine is taken by the patient. So the fifth class of drug is called as antihistamines, while the fourth one, blocking the release of histamine, is called as mast cell stabilizers. So these mast cell stabilizers, here you can see in this one, the mast cell degranulation inhibitors, they prevent the degradation of those granules, they prevent the release of histamines from those granules. And what happens, the histamine stay in the mast cells for a longer time and then slowly it gets metabolized. So the example of drugs, commonly these are the commonly used drugs. Among that, cromolyn sodium is commonly used as a mast cell stabilizers. They are used to prevent the release of histamine, but they cannot block the released histamine action. This is the difference between a mast cell stabilizer and an antihistamines. Mast cell stabilizers, they block the further release of histamines, right? They won't be further, next lot of histamine won't get released, won't get secreted, but whatever histamine has been already released, they will produce their effect that cannot be blocked by mast cell stabilizers. So that can be blocked by antihistamines. These antihistamines will block the release histamines by binding to those receptors, and the receptors won't be available for the histamines. So how histamines undergo metabolism, we can see in this diagram here. The L-histidine decarboxylase enzyme, it converts first histamine. The histamine undergo N-methyl transfer, or the enzyme is N-methyl transferase. This N-methyl transferase transfer one methyl group to the NH nitrogen of imidazole ring, and this N-methyl histamine formed, it undergoes to oxidation and formation of N-methyl imidazole acetic acid takes place. The enzyme is monoamine oxidase B. You know that there are monoamine oxidase A, monoamine oxidase B. Both are monoamine oxidase catalyze the different set of biochemical reactions. So the name as itself indicates, monoamine oxidase. So it will act here and oxidizing this part, CH2NH2 will become again CH2COOH. This is the one cell route of reaction. The another route of reaction is diamine oxidase, the histamine, it undergo oxidation and the formation of imidazole acetic acid. This is acetic acid attached to imidazole ring. Now this imidazole acetic acid undergoes ribose transfer reaction in catalyzed by enzyme phosphoribosyl transferase and formation of imidazole acetic acid riboside takes place. Now the question here is why the metabolized products will not show the effect as it has been shown by histamine. Now the simple answer here is if you talk about the drug receptor interactions or the theory of drug actions or theory of binding of a drug to particular receptors, your small variation in structure leads to drastic loss in activity. Drastic loss in activity is just because the change in or the introduction of a group on the drug molecule or particular molecule, it changes its ability, it changes its affinity for that particular receptor and the activity gets abolished. So for example, here histamine, and when we are introducing one methyl group here, we are blocking this hydrogen for interaction with receptors through hydrogen bonding, and because of that the affinity for binding to that receptor will be blocked and the effect of N-methyl histamine won't be same as compared to histamine. This is the simple rule for any drug receptor actions, for any drug receptor mechanism. So any questions from this slide? Please, if you have any query, ask now. Why Darshan left the class? Darshan J has left. Okay, shall we move to the next slide?
Yes, sir.
Yeah, okay, fine. So after this class, we should be able to answer these questions, correct? First was the histamine contains which heterocyclic nucleus? Yes, please answer me. We discussed what histamine.
Imidazole.
Imidazole. Yeah, remember histamine contains imidazole. See these points now very important because you may get questions in your MCQ. Histamine contains imidazole ring. What is imidazole ring? 5-membered ring with 2 nitrogen at 1 and 3rd position, first and 3rd position, right? If nitrogen is at 1st and 2nd position, what will be the name of nucleus? Pyrazole. Pyrazole. No, pyrazole. Pyrrole contains 1 nitrogen. Pyrazole contains 2 nitrogen, 1, 2, and imidazole contains 2 nitrogen, 1, 3. Correct?
Yes, sir.
Yeah, be very clear with the concept. Pyrrole, 5-membered ring with 1 nitrogen and hydrogen. Okay. Pyrazole, 5-membered ring with 2 nitrogens, and imidazole is 5-membered ring with 2 nitrogens at 1 and 3rd positions, right? So our histamine contains imidazole ring and 1 ethylamine at the 4th position of imidazole ring. Okay, now next question. Which is the precursor amino acid for synthesis of histamine? Yes.
L-histidine.
L-histidine, right? So L-histidine is the precursor amino acid for the synthesis of histamine. Remember this one. Then the third question is, what is the name of enzyme involved? Sorry, mistake here. I should be there. Involved in histamine synthesis. Which enzyme is involved?
Decarboxylase.
Histidine decarboxylase. Yeah, good. Now the fourth question. Histamine exists in how many tautomeric form?
2 tautomeric.
So, like no, they may ask you 1, 2, 4, 6. So histamine exists in 2 tautomeric form. How these 2 tautomeric forms are possible? Because of the shifting of intramolecular shifting of proton between 3rd nitrogen and 1st nitrogen. Clear? Yeah. And then the last question is, how many rotamers of histamine possible? How many rotamers? 2. Correct? Trans and gauge. Trans is due to the rotation of carbon, alpha and beta carbon with bond angle of how many degree rotation? 180 degree rotation. That is the trans rotamer form. While the gauge rotamer form is possible due to the rotation of 60 degree between carbon and alpha and beta carbon. Apart from that, we must know the type of histamine receptors. What are the types of histamine receptors? H1, H2, H3 and H4. And histamine binds to these receptors and produce the biological effect. So what are the different method of abolishing histamine effect is by decreasing the cellular uptake, by desensitizing the cell to histamine, right? We already discussed. Then by metabolizing the histamines, by stabilizing the mast cells, or you can say by inhibiting the release of histamines. And the fifth one, which is the actual topic of our medicinal chemistry, is by blocking the binding of histamine to its receptors, and that type of drugs are called as antihistamines, right, which we will discuss from the next class onward. So after today's class, we won't discuss any, like, we won't discuss about histamines. We directly shift to antihistamines, the types of antihistamines, classifications, structure activity relationship, and the individual examples. So before when you are coming for the next class, kindly submit the assignment of all these 5 questions which is displaying here on your screen. Okay, so please all of you have to write the answer for these questions and submit it to my mail ID. I think which is there in the previous first slide itself, KLEM Gmail. Everyone has to submit the assignment answer to my mail ID, and here is the mail ID, klemPharma@gmail.com. Okay, so if any doubt, please ask, clarify it, and so that when we are coming for the next slide, we will be like familiar with histamines, and we'll have a clear picture in our mind that okay, why we are going to design antihistamines. Any questions? Hello, any
No,
questions
sir.
from the?
No, sir.
Okay, so shall I conclude this class for today?
Yes, sir.
Okay, sir. Yes, sir.
Okay, thank you everyone. Stay safe and please submit answer of all these questions to my mail ID. This is your assignment first for this topic. Okay.
Okay,
Yes,
sir.
sir.
Thank you.
Okay, thank you.
Thank you.
Till that, goodbye. Take care. God bless you all. Thank you very much.
Thank you, sir.
Welcome.